Chemistry, dissecting the atom. Where are the electrons in atoms? There is a study guide accompanying this film strip which reviews the concepts of this part. Have you ever looked closely at a rainbow? Have you ever used a prism? This triangular-shaped piece of glass can take simple daylight and transform it into a beautiful rainbow of colors. Well, what does a rainbow have to do with electrons? 100 years ago, this would have been a legitimate question. However, since Niels Bohr, a Danish physicist in 1913, and later on with the help of higher mathematics, knowledge about light has allowed students of physics and chemistry to learn a lot about these tiny particles that cannot be seen even with the most sophisticated of instruments. First of all, are you aware that light is a form of energy? After all, why protect your eyes from the light of a sun lamp? How do you get a picture just by allowing light to strike some film through a camera lens? Isn't it true that plant life needs sunlight to thrive? If a prism is mounted inside an instrument called a spectroscope, you can observe what is known as the continuous spectrum of light. Sunlight is really white light, which is comprised of all the visible colors. Notice how each color runs or fades into the next. It has been found that each color of light actually corresponds to a different amount of energy. Of the colors red, orange, yellow, green, blue, indigo, and violet, violet is the highest in energy and red the lowest. Of course, there are energies of light which cannot be seen by the human eye. Ultraviolet light is such an example. This beautiful tan is a possible effect of being exposed to light corresponding to this amount of energy. Suppose instead of using your prism to look at sunlight, you use it to look at the red light given off by a neon sign. A neon sign is really a special tube made of glass called a gas discharge tube and is filled with a small amount of neon gas. The glass can be blown to take on any shape so as to spell words. You can look at the same type of tube in a laboratory. A high amount of energy, or voltage, is allowed to pass through this tube filled with pure neon gas, resulting in a beautiful red color. If you look at this through a prism, you no longer see the type of continuous spectrum you saw with sunlight. The colors no longer run into each other, do they? Rather, you see narrow bands of light separated by large dark regions. Why is this? Modern theory gives the following explanation. A neon atom has protons and neutrons in the nucleus. The protons are positively charged, while the neutrons are neutral. The negatively charged electrons are somewhere outside the nucleus and are held to the atom by the attraction of the protons, somewhat, although not exactly, in the manner that the Earth is attracted to the Sun. Each electron has found some general region outside the nucleus where it is most stable. The electron is happiest moving around here, and unless disturbed by some outside force, it is likely to stay in this region. This most stable region is called the ground state of the electron. If you now turn on a high voltage, which is really a stream of high-speed electrons, you can give the stable neon electrons a real jolt, much as a tennis racket jolts the ball over the net. The electron is no longer in its stable ground state. The electron is said to have been excited and is now in an excited state. This is some specific region farther away from the nucleus than before. The electron has absorbed or taken in a certain amount of energy in order to jump into the excited state. The electron will immediately return to its ground state in one or more steps. As it returns to its ground state, the electron emits or gives off all the energy it had absorbed when it had originally been excited. It gives this energy back in the form of light. Since each color corresponds to different amounts of energy, what you see in the neon spectrum is a measure of the various amounts of energy given off. But why doesn't the neon spectrum look like the sunlight spectrum? Perhaps this diagram will help explain the currently accepted theory. Here is one of the electrons outside the nucleus of a neon atom in its ground state before the high voltage is turned on. Each of the other lines you see farther away from the nucleus corresponds to another possible energy region where an electron may be found. An electron can be found only, repeat, only, in one of these regions and in no area between them. Okay, let's turn the juice on. The electron has now been excited to some higher energy level. Which level? That depends on how much energy it absorbed. The harder it's hit, the farther it goes. The different color arrows show different regions into which the electron could have gone. Again, notice it must go into a definite energy region and not just anywhere in space. Now the electron immediately gives off the energy it has just absorbed and is returning to its most stable or ground state. Notice that it can only return by falling into one of the definite regions shown. Much as a ball would drop down a staircase. After all, can the ball stop here? Why then, when you look at the red neon light through a prism, don't you see all the colors running into one another? The reason is that each color corresponds to definite amounts of energy, which have been given off by the electrons as they fall from various excited states back to the ground state. Each arrow that you see in the bottom diagram will correspond to a different color of light. The dark regions you see in the neon spectrum correspond to amounts of energy which are not given off by the electrons as they fall towards their ground state. The same type of result holds true for any other gas when placed in a gas discharge tube. The hydrogen gas discharge tube gives you a result like this. Gaseous mercury shows still a different spectrum. They all have a common factor, as you've noticed. They all show very narrow bands of light corresponding to very definite amounts of energy being given off as electrons return to their ground states from various excited states. Remember, too, this is a theory. If you could actually see electrons, you wouldn't need theory to discuss where electrons are. You don't need a theory to explain where Joel is. You can see him. You don't even need a theory to explain approximately where the planets are in the solar system. They can be seen either with the naked eye or with the aid of a telescope. Electrons are another story, however. If you can't even see atoms under the high-powered electron microscope, you certainly aren't going to be able to see the minuscule electrons which make up only a portion of the atom. However, spectroscopes, higher mathematics, and some great minds have been trying to let us see the light. If your course of study does not include the concepts of orbitals, subshells, and probability, look at film strip number 7, Energy Levels and Electron Dot Diagrams, next. For those of you who will be learning this material, continue with film strip number 4, Shells, Subshells, and Orbitals.